Numerical Series 6, a rigid insulated tank is initially evacuated. It is connected through a valve to a supply line that carries air at a constant pressure and temperature of 250 kilopascal and 400 Kelvin respectively. Now the valve is opened and air is allowed to flow into the tank until the pressure inside the tank reaches to 250 kilopascal, at which point the valve is closed. Assume that the air behaves as a perfect gas with constant properties Cp equal to 1.005 kilojoule per kg Kelvin, Cv equal to 0.718 kilojoule per kg Kelvin, R equal to 0.287 kilojoule per kg Kelvin. Final temperature of the air inside the tank is dash Kelvin. Round off to one decimal place. So in this question here we have to calculate final temperature of the air inside the tank. So before we solve the given numerical, let's briefly discuss the approach we will be using. So for that, let's draw a supply line along with a rigid insulated tank . So the tank is insulated from all the sides . So this is the tank and this is the supply line. The mass of air enters into the tank from supply line by means of a valve. So this is valve having pressure 250 kilopascal and temperature 400 Kelvin. Now the flow of mass into the tank from the supply line continue until the pressure inside the tank reaches to 250 kilopascal. So this is mentioned in the question. So here we have to consider the flow of mass into the system or into the tank as mentioned in the question, but there is no exit section is mentioned for the given case. So we understand it is a case of unsteady flow. So we consider it is a case of unsteady flow. So here we are going to use the unsteady flow energy equation to solve the given numerical. Now why we consider this is a case of unsteady flow? Because there is an accumulation of mass as well as energy within the tank. So according to the unsteady flow energy equation, rate of accumulation of energy within control volume must be equal to net rate of energy flow across the control surface. So the expression of unsteady flow energy equation can be written as del EV, that is equal to MI HI plus VI square by 2 plus ZI G plus Q minus ME HE plus VE square by 2 plus ZE G plus W. So this is the expression of unsteady flow energy equation. So to understand the unsteady flow energy equation, we have to consider inlet condition of the tank, and the inlet condition is denoted with subscript I. So this inlet condition represents what? It represents what amount of mass or what amount of energy is flowing into the tank. Then we have to consider the exit condition of the tank. So the exit condition is denoted with subscript E. Next we have to consider initial condition of the tank. So this is represented with state 1. So it means in the beginning we have to consider what is the mass within the tank, or in the beginning what is the energy within the tank. So that initial condition is represented with state 1. Next we have to consider the final condition of the tank. So this is represented with state 2. It means if we consider the flow of mass into the tank, it means after flowing, or you can say after filling the tank, what would be the magnitude of mass within the tank, or what would be the magnitude of energy within the tank. So that is represented with state 2. So let us consider initially the mass within the tank is M1. So this is the mass which is initially or here we consider that is initially mass present within the tank. And let's consider M2, that is the mass after filling the tank. So this is M1, that is the initial mass, and this is the final mass after filling the tank. So if we consider what is the net amount of mass entering to the tank, so that is denoted with Mi, that is the mass which is entering to the tank. It means here we consider this Mi to be M2 minus M1. So this we have to keep in consider or keep. So this we have to consider while we solve the given questions. So here we have considered the unsteady flow energy equation. So in this expression, we will see here that this expression consists of inlet condition as well as exit condition. But as earlier we discussed that there is no exit section mentioned in the given question, so we have to neglect the expression of exit section, that is MEHE plus V square by 2 plus ZEG. And the work done, there is nothing mentioned regarding work done on the system or by the system. That's why we also neglect this W term. And here in this question, it is mentioned that the tank is perfectly insulated. It means there is no heat interaction between the system and surrounding. That's why we consider this Q to be 0 here. And another thing we have to consider in the inlet section, that in the question it is mentioned that the mass is entering. So if mass is entering, it means that mass must have some enthalpy. But there is nothing regarding kinetic energy and potential energy which is mentioned in the question. So we simply neglect this kinetic energy and potential energy here. So the equation of unsteady flow energy equation reduced to del EV equal to MIHI. And see, this del EV is nothing but that is the accumulation of energy within the insulated tank. So here we have to assume that the internal energy is accumulated within the tank and there is nothing regarding kinetic energy and potential energy. So we have to neglect the kinetic energy and potential energy within the tank. So here this del EV is written as del U, only internal energy we have to consider. So that is equal to MIHI. Now this del U is nothing but that is final internal energy minus initial internal energy is equal to MIHI. Now see, here we have written this U in capital form. It means it is considered the only internal energy. But we have to consider it to be specific internal energy. So we have to write down this capital U in form of small u. So to consider small u, we have to consider that small u along with mass. So it becomes M2U2 minus M1U1. That is equal to MIHI. Now see, in the question, it is mentioned that initially the tank is evacuated. It means initially there is no mass and there is no energy present within the tank. So this we have to consider that tank is initially evacuated. It means no mass or no energy remains within the tank. So here we consider the initial energy, that is let that energy to be the internal energy. So U1 must be equal to 0 and M1, there is no mass within the tank initially, so that we consider M1 equal to 0. So here we consider this expression as M2U2 minus M1U1 is equal to, in place of Mi we substitute M2 minus M1 into Hi. Now what is this Hi? Hi is the initial enthalpy of the mass with which the mass flows into the tank. So here we neglect this M1 and U1 term in the left hand side, and in the right hand side we neglect this M1 term. So the equation reduced to M2 U2 is equal to M2 Hi. Now see, M2 is present in both the sides of the expression, so we cancel this M2 from both the sides and it becomes U2 equal to Hi. It means we can say that the final internal energy within the tank is equal to the initial enthalpy with which the mass is entering into the tank. And we know that U is equal to CVT and H equal to CPT. So in the question, the value of CV and CP is mentioned. So we have to use this value of CV and CP to calculate or to further calculate this numerical. Let's consider U2 as CVT2, that is equal to HI, that is equal to CPTI. So T2 is what? T2 is the final temperature of the air after filling the tank. So this T2 we have to calculate here, and Ti is the initial temperature, or you can say the inlet temperature of air which flows from supply line to the tank. So the CV value is given, that is 0.718 kilojoule per kg Kelvin into T2. This we have to find out. CP is also mentioned, that is 1.005 kilojoule per kg Kelvin into Ti, that is mentioned as 400 Kelvin, which is given in the question. So after solving this equation, we get the magnitude of T2 is equal to, that is 559.88 Kelvin. But in the question it is mentioned that round off the calculated value of temperature, the calculated value of final temperature to 1 decimal. So after round off to 1 decimal, the temperature or the final temperature of air within the tank is equal to 559.9 Kelvin. So this is the final answer. Thanks for watching. See you in the next video.